Hello, everybody. Thank you all for coming out tonight. My name is Zach Parrish. I'm the programming librarian here at the Bexley Public Library. Before we get started, I just want to give a quick couple of notes on how tonight's program will run. This is a hybrid program, so thank you all for coming out to the library tonight, but we do have an audience viewing at home. So when we get to the end, if you have any questions, if you don't mind raising your hand, I will bring the mic over to you. That way those watching online can hear what is asked in the room. And then for those of you who did come out, fingers crossed if it stays clear, and if the moon gets high enough, we will have telescopes out in the parking lot afterwards. So if you're interested, stick around afterwards, and we'll meet out there for some stargazing. Before we get started, I do want to highlight a few programs we have coming up at the library. If you're unaware, this year is the Bexley Centennial, or the Centennial of the Bexley Public Library. So we have a wonderful author series that we've put together. And next Thursday, July 25th at 7 o'clock, we have Linda Cass, who is the owner of Gramercy Books right across the street, and the author of her most recent book is called Bessie. She will be in conversation here with Columbus Metropolitan Library Director Patrick Lazinski. Again, that's next Thursday at 7 o'clock. You can attend in person or online. And then we have a wonderful series coming up in August celebrating James Baldwin at 100. So James Baldwin's 100th birthday would have been August 2nd this year. And so we have 3 programs. The first is a screening and discussion of the documentary film I Am Not Your Negro, and that will be facilitated by Cynthia Young, who is the chair of the Department of African American and African Studies at OSU. That is Saturday, August 3rd at 3 o'clock. And then we have a book discussion of James Baldwin's If Beale Street Could Talk on Sunday, August 11th at 2 o'clock. And we're wrapping up that series with Ohio authors Prince Shakur and Cortez Harris, who will be in conversation discussing James Baldwin's legacy and his influence on their work. And that is on Thursday, August 29th at 7 o'clock. Tonight's presenter is Jack Stetham, who is an undergraduate at The Ohio State University, majoring in astronomy and astrophysics and physics, and he will be discussing some of his current research on neutrinos and machine learning. So I will turn it over to Jack. Thank you all for coming.
Hello, is this working? Cool. So yes, as Zach said, I will be presenting on astrophysics and AI. I'm actually going to split this up into 2 sections. So I'm first going to talk about AI and what it is, kind of a general overview, and then I'll go more into my research. After I'm done talking about AI, I'm going to ask for questions, because I think it's a good stopping point if you guys are curious or want to know more about general AI, and then I'll have another set of time segment for questions after I'm done talking about my research. So let's begin. So a little bit more about myself. I'm a physics undergraduate student at The Ohio State University. I'm a rising senior, and I'm a student researcher as well. So I work in actually both departments, the physics and the astronomy department at OSU. And I work with Dr. Richard and Kaylee Hughes, their father and daughter. And we work on astroparticle physics research. So basically, we study subatomic particles that come from outer space. They could come from a bunch of different sources, and I'll talk more about that later. But I work on that with them. And then with Dr. Christopher Kochanek of the astronomy department, I study rotational variable stars, which are just stars that are kind of odd. They've got a weird periodic display of their light, and we're kind of interested in them. I'm also a programmer, so I worked on the all-sky automated survey for supernova. You can call that ASSASSIN for short. It's kind of a nice acronym. And basically, this array of telescopes dotted all around the world constantly scans the sky and provides astronomers with valuable information to perform their research. It's actually what I'm using to study rotational variable stars. So I worked on the code that revitalized this from an older model to a newer model. And then for one of my projects in my upper level physics courses, I created an AI model that actually finds Waldo in the Where's Waldo text or children's books. I was kind of at a loss for what I should do for this project because everyone was doing like super cool finding galaxies in this section of the sky or like facial recognition. I was like, oh, I just want to find Waldo. So it turned out to be a pretty fun project. I'm also a brother of Triangle Fraternity, which is a STEM organization on campus. And I was the former vice president and now alumni chair. And I'm also, for a non-STEM activity, because I know that was a lot of science stuff, I am a guitarist for my band Red 40. So what is AI? AI stands for artificial intelligence. But personally, I actually never use the word artificial intelligence in any of my research. I prefer the acronym ML, which stands for machine learning. Truthfully, you can say anything. In any conversation with someone about AI or ML, you can say either. AI is just more popularized. In actuality, there is a difference. So artificial intelligence is the actual ability for computers to simulate human thought and perception, whereas ML, machine learning, are the physical tools that we use to allow for the simulation to happen. So it's more of like a subcategory of AI. Just as with anything that's automated, it basically performs a task that once required humans to do, and now doesn't require it. So I've got some pretty cool examples of generative AI that I think will help visualize what AIs can do. So here we have some image generation. Here, as a note, I did not make any of these. This is all done through computer simulation. All I did was give a prompt. Actually, Wayne liked the raccoon, so he gave this one the prompt. But here we've got some raccoons playing with a Ouija board underneath the night sky, observing the moon. And then we also have some raccoons in some tie-dye shirts sitting discussing some astrophysics papers, resembling our daily astrophysics coffee notes. I've also got some examples of text generation. So who here has heard of ChatGPT? Maybe? A lot of people. It's probably the most popular text generation AI out there right now. So here I give a prompt, please write a birthday card to my sister. Now I would never do this, of course, because I care a lot about my sister, and I would write here something very heartfelt. But if I was in a pinch, I could just ask ChatGPT to write this for me. And look, here, it's a great prompt. Dear, I'd have to fill out the name, but I don't think I could tell. I mean, this isn't how I'd write a birthday card, but I don't think I could tell that this is AI generated, honestly. And then on the right, we have another model called Google Gemini, which I give the prompt, explain the difference between squirrels and chickens. That's pretty easy, right? Chickens have 2 legs and squirrels have 2 legs. Wait, maybe I do need an AI to figure this out. So basically, first it takes the prompt and it classifies the squirrels and chickens into their respective types of animals, birds, rodents. Then it gives us a description of diet, habitat, movement, behavior, domestication. All this information was given to me by just saying explain the difference between squirrels and chickens. Now you'll notice these 2 types of prompts are very different. I ask Google Gemini to explain the difference between something, and I ask ChatGPT to specifically write out a long-form content. This is playing to each model's strengths. So Google Gemini is much better at resembling something like a Google search, where you're asking for output information, whereas ChatGPT is better at long-form content. So you ask it to write something filled out, like write a research paper about blank, or write a resume, or edit my resume. So these are playing to each model's strengths, which is something you can fine-tune when you actually are creating and training the AI, which I'll get more to later. I've also got some pretty cool videos as well. So much like with text and images, you can generate videos. So here's the first one.
Step into the incredible world of The Incredibles, where heroes come in all shapes and sizes. Meet Bob Parr, once the mighty Mr. Incredible, now striving to live a quiet suburban life. By his side is Helen Parr, formerly known as Elastigirl, whose flexibility goes beyond her superpowers as she juggles family and heroism. Their family is no ordinary one. Violet, their daughter, can vanish in the blink of an eye and protect her loved ones with force fields. Dash, their son, is faster than a speeding bullet, always ready to outrun any trouble. And let's not forget little Jack, who's full of surprising abilities that keep everyone on their toes. But that's just the beginning. Meet the no-nonsense superhero fashion designer Edna Mode, who ensures every costume is as functional as it is fabulous. Then there's Lucius Best, known as Frozone, whose icy powers and cool demeanor are always a breath of fresh air. Lastly, we have Buddy Pine, who once idolized Mr. Incredible and now emerges as the tech-savvy villain syndrome, bent on proving that anyone can be super. So strap in and prepare for a roller coaster ride into the incredible universe of The Incredibles.
So that video was actually trained on, I mean, I'm sure you could guess, The Incredibles, the movie, but also a series of 50s style movies. So once again, that was all generated. No one made that. That was a prompt that was typed in to an AI, and that was the output. I also have a couple examples from OpenAI's in video generation. So OpenAI is the same company that made ChatGPT. So here we have some dogs playing in the snow. I'm pretty sure the prompt was just golden retrievers playing in the first snow. And it produces very high quality images. I mean, you saw in the other video that it was maybe less quality. That could be a result of the 50s style. But this is extremely high quality content. And then this unfortunately is not always great. So you could type a prompt in and it doesn't perform very well. And here's an example of that, where you have a bunch of wolf puppies and they seem to actually be popping out of each other and multiplying randomly. So it doesn't always go to plan, but for the most part, it's pretty cool, right? Then my favorite example actually is songs. So you can take a song, take out the voice of the person whoever's singing it, and put in someone else. So who here knows Eminem? Okay, who here knows Frank Sinatra? Okay, get ready for this.
His palms are sweaty, knees weak, arms are heavy. There's vomit on his sweater already. Mom's spaghetti's nervous, but on the surface.
So a man who's dead is singing Eminem. It's pretty cool. It's pretty cool. I mean, realistically, I don't know who would have a use for this, but it's pretty cool. Now, I guess to see some more examples, I guess I could ask, does anyone have any prompts they'd like to give or try out on a ChatGPT? Anything? Any ideas? No? Come on. Yes?
What do you prompt ChatGPT?
Okay, that is a great idea. And unfortunately, with code, ChatGPT is not the greatest. What all these models are built off of is this long pipeline of libraries called TensorFlow and PyTorch, which is some random code languages, but it doesn't have those available, but that is a great idea, and I like how you're thinking. Does anyone else have any small ideas? Yes?
Write us a research paper on gravitational wave telescopes.
Oh, okay, sorry. Would you say gravitational waves?
Wave telescopes.
And look at how fast this is. This is crazy, right? I think this is ChatGPT 3.5, so this is the older model. ChatGPT 4, which is just released and you actually have to pay for. This is free, by the way. Anyone can access this. ChatGPT 4, which you have to pay for, is even better. And it's actually good at handling code, so you might be able to write ChatGPT with ChatGPT. But yeah, I mean, it's got laser interferometry, detections of gravitational waves. Oh, it talks about LIGO. That's pretty cool. And that's a big thing in gravitational waves. So it seems like it knows what it's talking about. That was a good one. Thank you. Yes, one more?
How do you know that what they're writing is actually accurate?
Well, I'm impressed that it's mentioning LIGO, Virgo, and Lisa. Those are actual like projects that are well known.
That's well known to you.
Yes, that's fair.
I'm just an everyday,
Mhm.
not so normal person. How, if I were to put that in, it's a great prompt. I'm reading this, it's like, okay.
Yeah.
It could tell me something totally random, and I have no way of knowing, you know, you say to fact check it all. If I have to fact check it, then what's the point of this? And yet you're getting stuff that may or may not be accurate.
Yeah, that's absolutely fair. And I think it all comes down to how you're utilizing this. So you shouldn't ask something like this, honestly. If you want to learn more about, learn more in depth about a topic, you could ask this for pointers and then go out and find real research papers that talk about this topic. But you, in reality, shouldn't trust anything that's AI generated. Yes, Wayne? It'll give you works cited. It's fake, and it doesn't actually cite real things, but it'll give you a works cited. It'll make up random ones to, when you say, hey, cite this paper, it'll just make up random things. So you cannot, yes?
Are numbers randomly generated by ChatGPT and other AI actually random, or is there?
Random number generation is kind of a problem in itself because when you ask for a random number, it's never actually random because it's computer programmed. So technically, no. That problem still exists here. OK. Yeah, but here's some examples. I'm glad you guys got to try things out. I'm also going to talk about a couple other types of AI. So we saw generative AI, which is what ChatGPT, the image generation, all that stuff is generative. There's other really powerful and impactful models that I use in my research. So there's classification models. Let's say you give an AI some pictures of cats and some pictures of dogs. Hopefully, cats and dogs are different enough to this AI model that eventually, when you ship it off and give it to someone to use, it can actually determine, oh, this is a cat, this is a dog. Regression, it's the same thing as like slope-intercept form, y equals mx plus b. It's just predicting a value. So if you associate colors with types of balloons, if you associate numbers with colors, so let's say you have a red, green, and blue balloon, and then you have colors 1, 2, and 3. You give the model these numbers, and it predicts what number it should be after looking at the balloon, if that kind of makes sense. It's just predicting a value. Then you have evolutionary AIs, which are the same thing as, who's the evolutionary guy? Darwin, thank you. Yeah, it's the same thing as Darwin, where you give two parents certain traits, and you weight the traits with how important they are, and then the two parents will create babies, basically. And then these babies will have features associated with them, and the good features will be highly weighted, and the bad features will not let there will be a cutoff where the babies with bad features won't be allowed to continue reproducing. So eventually, you get the most optimal subject. We do this with antennas right now in a really popular project called Genetis, where they take two parent antennas, run it through an evolutionary model, and then eventually you have an antenna that's the best of both worlds. OK, so I keep talking about you're feeding in this information and you're getting out this information. Well, what's actually in the black box? The way I like to view AI is like a sandwich. It seems rudimentary, but it's a great analogy. So basically, you have your input layer, which is the top piece of bread. And then in between your pieces of bread, you have these different layers, these different condiments, or whatever you want to put on your sandwich. So here we have lettuce and onion and turkey, which, I don't know, maybe that's a lame sandwich to you guys, but I feel like it's OK. But every individual layer has a table associated with it. And in this table is a bunch of numbers. So here, it's all A, but that can be any number. That's a variable for any number. And each layer has its own set of numbers. So when you're training this model, or you're preparing it, you're giving it information. It could be images. So you're feeding images into the top layer of bread. And these layers within the pieces, the values in these tables for each layer are constantly changing as it's training. It's taking a set of the data that it takes in and calculating how good it is at each moment and changing the values of the table until it's as best as it can be. It's maximizing how good the model can be. So this entire process of training is essentially changing these numbers in the table until the output is as good as it can be. Once it's as good as it can be, we smack the sandwich together, put it all together, and ship it off. And then there's no longer any changing of the numbers. The values are set. The weights are set. We call these weights. They're set and can be used for production. So now when you give an input, it'll just give an output. I hope that's the sandwich analogy is good enough. Here's some practical uses of AI as well. So generation's cool, but in reality, it's not as applicable to our daily lives. So we have image and facial recognition, which you guys have on your phones. You know when you open up the Photos app, how sometimes albums form based on certain people? That's facial recognition. Medical diagnosis. So let's say you have a set of x-rays, right? And you know beforehand that this bone is broken in the x-ray. You could train an AI to feed in x-rays, look at the x-ray, and then predict which bone is broken. Customer service. Let's say you want to go talk to someone about a certain product on a website, but no one's answering you. You could have an AI that knows the products, is trained on past conversations with customers and customer service representatives, and it'll respond to the customer for you. Recommendation systems. You ever talk about a product and then it shows up on an ad like 30 seconds later? It's the same thing, but way better. And then transportation, self-driving cars, pretty cool idea. I think Tesla is in the lead right now with their, either Tesla or Volkswagen. They also have a good self-driving car. But so there's some practical applications. Now, as you mentioned, there's problems with AI too. One of the big ones is lack of transparency. So these models are hard to understand, and because they're hard to understand how they're made, they lead to miscommunication about what you should trust. They lead to in essence, a little bit of fear-mongering. But the difficulty of understanding technology is a problem that's existed for as long as we've been improving technology. So the only thing we can really do to combat this is just education. So bias and discrimination as well. The model, the sandwich, is made based on your input data. So if you give it biased data, let's say you train a model to talk about football, and your input data is conversations from OSU students. That AI is going to be great. That AI is going to be awesome. But let's say you train a model based on Case Western students. That model might not be as good. Maybe, I don't know, but probably not. So yeah, you got to be wary of bias and discrimination. Then there's overdependence. The great thing about AI, and generative AI at least, is that it provides a low barrier of entry to start working on a project or start studying something. But you can't become dependent on utilizing that for all your information. And if you consistently use an AI to produce work, eventually when you come across a problem that requires a real human and real complex analysis and real critical thinking, you won't be able to do that. Privacy concerns as well. So when you talk to ChatGPT or Google Gemini, it is recording that information. It stores that interaction in a database, and it uses that for future training. Do not put your private information into an AI, please. No social security, no credit card information, nothing. It's dangerous. And then job displacement as well. So as with automation, the unfortunate reality is that automation lessens the amount of jobs available for jobs that can be automated. Now I will answer questions about AI. Yes?
So, a couple of months ago, I think there was an
Mhm.
What kind of like mechanism, what kind of like coding was that affecting that, and how was it like fixed?
Yeah, so the issue with, that's an issue with bias and discrimination, right? That is a problem with the training set. The actual code doesn't do anything. The code is written by a bunch of programmers in a room in some Google building or whatever, right? The actual problem comes from the type of data you're giving this model to train, because it's all the same shell, right? Every model, with some respect, is the same empty sandwich. So the issue is the type of data you're giving it, and if you want to combat that, you need to rethink and relook at the type of data and where you're getting it from. Yes, in the back?
So the input, the sandwich that you showed.
Yeah.
And you talked about the input, the different layers and output. So does it then cycle back around where the output then cycles back into future input, future layers, and future output, building on itself in a continual loop?
Yeah, so during the training process, it is continually doing that. That's what we call an epoch, or an iteration. And it does that continuously until it realizes that it's done the best that it can. And then you collapse the sandwich and send it out. And then once you send it out, there's no more changing of that sandwich.
There's no more
Looping, no more looping.
information that's out there.
Yes.
Where does that go?
Or sorry, the information is where?
The information that's in the output never comes back to train further.
Mm-hmm.
I mean, so you want something from you get the output.
Yes. Yeah.
But since AI trains on itself, the output doesn't then feed back in. Like, it could be a never-ending. I could be infinity. I mean, how does it ever stop?
Yeah, so there's essentially different phases. There's the training phase, and then there's the production phase. So during the training phase, you're right, it continues to cycle. But once it's realized that it's done training, the creators, or whoever's working on it,
They push the stop button.
yes, they push the stop button. They say, OK, we're pushing this out to the public. They can use it.
Okay, right. And then they're never going to say, okay, take that out and put it back in.
No.
Okay, and then the other thing is, I know you talked about privacy, and don't put your stuff in there, but we put our information into healthcare,
Mm-hmm.
portals, et cetera, and how do we know that stuff is not already out there? I mean, somebody can just use it when they want to use it. I mean, like, I'm thinking privacy just doesn't exist anymore.
I mean, that is kind of true. But I mean, it's really just about mindfulness, and just in today's age, yeah, you really can't escape not having any piece of your information out on the internet. But trying to reduce that as much as possible is really important. Yeah, yeah. Don't panic, though. It's not, yeah. Any other questions? Yes, yeah, in the front.
So, we know about ChatGPT. We know about ChatGPT and heard of that, and the other one that you talked about there. I guess trying to get an idea, get my mind around how many products there are out there. Are they continually being generated? And I suppose some have specific uses, like the medical and like research and that kind of thing. Is there thousands or hundreds of thousands of these products that people are using these days, or
Yeah.
What's that look like?
So it depends on whether we're talking about public access or private. There's definitely less available for the public. Companies right now, though, are on the bandwagon of, we need AI in this, we need AI in that. And honestly, there's a lot of places where you don't. But they like the buzzword of AI, and they like it to sell to investors. But I would say that probably 15% of the things that are out there, the AIs that are made, are public, and then the remaining 85% is private. But number-wise, I mean, it's constantly changing, because I could make something right now. I mean, I made Waldo in like 2 weeks, and anyone can use it. If you guys want it, let me know. Just email me. But anyone has the capability of making something like that. So the number's constantly increasing. Yeah.
Really quick, because of your question, there's another generation or like text generation called Perplexity AI, and it actually shows you which sources that it is pulling from. So
that's cool.
if you're it's better with like lists, not so good as like writing a birthday card. But yeah, if you're using it for like generating a list or starting research, it'll actually show you what it's pulling from.
Hi. So you answered that question talking about how companies are using AI more. I work in digital marketing, and my company's had me use it for some instances, not a lot. And I was curious with OSU and I guess campuses, do you see it being used in the classrooms more, or even teachers like allowing students to use it more?
Well, I definitely think that if people, you love this question, don't you? Professors and teachers are going to have to adjust because it is there, it is open access. I would say that my professors are late to the game, to say nicely. They don't really, not that they don't understand, but they don't see how it is actually beneficial for education. I remember when I was studying for exams and I had to go over proofs about blank and electron degeneracy pressure and all this stuff for my exams. I was like, okay, I don't remember these proofs, and looking them up on the internet is a nightmare because it's just some like a picture of random chicken scratch on the internet. So being able to look up, hey, this is exactly the proof I need, please go step by step, that's really impactful and really beneficial for a student. I know Apple is releasing their calculator AI, which if you have an Apple Pencil and any Apple device, I think it actually is available on the phone too, but you can write any sort of math equation and it'll solve it for you. I believe it's like allows for integrals and derivatives and anything calculus-based too. So within OSU, not yet, but I hope that people start to realize its power.
What programming language do most AI run on, and why did they choose them?
I do just about everything that I can on Python. There's some things that I use C++ for reluctantly, but Python is like the overarching machine learning language. You could get into MATLAB, but don't. It's not good. Basically, everything I use is Python, and then the libraries that are really just built for making models, TensorFlow, and then Torch or PyTorch.
Okay, so say you're going to write a paper, you're going to publish a paper on gravitational waves. How do you cite your references? How do you give credit in the footnotes to your sources and your references?
I wouldn't put my name on an AI paper. So that's, again, back to like not being over-dependent on an AI to provide all your information, and just being kind of always skeptical because there could be bias in it as well. But I would not publish a paper that's been generated by AI, and I don't know if researchers really would because it's not your work, right? So as opposed to citing it, I guess you could cite the AI and cite OpenAI, whatever company created it. But I don't know if it would really be considered valuable research work in like an article or a journal. Okay, I think we have time for one more question because I'm also going to talk about physics and astrophysics.
Okay. This may just be an example of a problem, but in terms of overdependence in the healthcare field, I think what's happening is that AI is now looking at pathology slides or pap smears and so on, and in theory, making more accurate, dependable diagnoses. Is that an overdependence example, and what is healthcare going to be doing about that? Are we speculating who signs off, and you know?
Well, I'd say with overdependence, hopefully people who know about pap smears and like who are doctors are able to like read it and agree with the result. it should, in regards to the medical field, I think that it should probably be as like a flag indicator rather than like signing off, oh, you're gonna get this surgery as a result of this test. I feel like that, if you allow for everything to be automated, that would definitely be an example of overdependence. But what I've been talking about more is overdependence on information. So not depending on an AI to do everything for you and get all your information. You need to develop skills yourself, especially in the medical field. OK. Thank you for all your questions. I'm going to now move on to what I actually do in pretty much this entire summer. I've been working on it since February or so. But applications to astrophysics, new VIT, that was my own acronym, and UHE neutrinos. So new VIT stands for neutrino vision transformer, and UHE neutrinos is ultra high energy neutrinos. I'll go much more into that, but first a basic review of the atomic structure. So in the nucleus, we have protons and neutrons. They're roughly the same size. And then we have electrons, way smaller, way smaller. Neutrinos are smaller than electrons. So they're subatomic particles. They're super small, super low mass, 1,000,000 times smaller than an electron, actually. So very small. There's actually trillions that pass through you every second. Don't worry, it's OK. But the sun throws trillions of neutrinos that pass through Earth, they pass through us. Very rarely, they might interact with an atom in your body, but probably not. And if they do, it's OK, don't worry. But they're neutrally charged, just like neutrons, and ultra-high energy neutrinos are incredibly high energy. So we're talking greater than 10 to the 15th EV. EV is just a measurement of energy. Why do we care about these ultra-high energy neutrinos, though? Well, they are great messengers from crazy cosmic bodies. So things like galaxies, things like supernovas, which are like an exploded star, and gamma ray bursts, which is just another astronomical phenomenon. They act as great messengers. Why do they act like great messengers? Well, they're small, and they're neutrally charged. So they travel through space unaffected by everything else going on there. So they just straight shot from the source. But what is great about them also kind of sucks, because then it's really hard to detect. So they go through space undetectable by, or unperturbed by other things in space, and then when they finally get to Earth, we actually want to find them. So I work on applying AI to finding these neutrinos. I saw you had a quick question.
Do they not interact because they're so small?
Not interacting as in they're neutrally charged. So they don't interact with the electrostatic force at all.
Why do they pass?
Because they're very small. OK, so what is a VIT, or a vision transformer? It is technically an AI, or I would say it's a piece of machine learning. And it uses this special idea called embeddings. Embeddings are essentially associating a piece of information with a set of numbers. So here we have the word walked and walking. We give a transformer these words and the context that they're in. That's our information. And they associate numbers that are close together in space. And then we give swam and swimming and the context that surround those words, and they're also close together in space. So you start to see relationships between things as you give transformers more information. And these embeddings are the physical representation of where this information is and how close it is to other information. So instead of using words, we use images. That's why it's called vision transformer. Basically, instead of calculating calculating the context of a word or what is surrounding a word in a sentence, we take patches of images. So we take an image, we split it up into little segments, and then we calculate a number. It's called tokenization. but we calculate a number associated with these patches, and then after that, those numbers are calculated with the patches, it puts it all together and ships it out, and we do this for a bunch of different images. So in the end, we have images that are represented by a bunch of numbers. So how do we use this vision transformer? What are our images? Well, first, you got to go to Antarctica. So we have this balloon experiment called ANITA-3, which flew for about 40-something days, and it's got 48 antennae on it. We send it up, flies around Antarctica, collecting data. What data is this? So neutrinos, as I said, are neutrally charged, weakly interacting, and very small. But sometimes, very rarely, they'll collide with a particle. And when they collide, they create this cone of radiation. And we are detecting the radiation. The radiation is light, just like we're seeing now, but it's radio frequencies as opposed to visible light. So our balloon, it's up in the sky, it's reading measurements, and it's reading this radio frequencies. Here we can see some actual data plotted. So up above, we have two antennas, antenna 21 and 22. They're not special, I just chose them randomly. But this reading from 0 to 800 is the time in nanoseconds that this event is reading the radio frequencies. And then on the left, we have a voltage scale. So basically, the wave oscillates up and down, just like a light wave, and we're reading that here. To make our images, we do this special math called cross-correlation, which don't need to know anything about it, but it's just special multiplication. And from it, we are able to make these things called correlation maps, which give us sort of a probability distribution of where a particle is, where it's colliding in Antarctica. So on the left, we have a neutrino. The way to read these maps is it's basically just the sky, but put into a rectangle. So the bottom axis is the azimuth. Azimuth is like cardinal directions. So you have north, south, east, it's north, south, east, west, and you're just rotating around in azimuth. And then your zenith angle is, if you look straight up, you begin to slowly, slowly, slowly teeter down. That's your zenith angle. So it's from top to where you're looking at, if that makes sense. So you should have 0 to 180 degrees for this field of vision, and then your entire rotation is 360 degrees. So on the left, like I said, is our simulated neutrino, or sorry, is our neutrino, and it's interacting with the ice at 150 or so azimuthal degrees, and then a zenith angle of about 100, so it's below the horizon. 90 would be the horizon. And then on the left, we have a background image. So there's no neutrino here at all. So what we would do is give our vision transformer these pieces of information and say, hey, that's a neutrino, this is background, distinguish the two. The left is actually simulated. This is because we have not seen any yet. They are very, very, very rare. We know that they happen and that they come out of cosmic events, but we have not been able to see any with our radio antenna. So what we have to do is we simulate these, and this simulation is a little too good. This neutrino probably wouldn't happen. It's really, really high energy, but it's good at describing what a map would look like. But we give our vision transformer this, and we're able to classify, hey, we found a neutrino or we didn't find a neutrino. That would be a type of classification. On top of determining, hey, we found a neutrino or we didn't, we can take the images where we think we found a neutrino, and we can classify it based on flavor. So this is a cool part of subatomic physics, but particles have flavors, just like ice cream. I don't know why they call it flavors, but I kind of like it. I think it's fun. But you have electron, muon, and tau neutrinos. The only really important difference is that tau neutrinos are heavier than muon neutrinos, and muon neutrinos are heavier than electron neutrinos. and tau and muon decay into electron. Everything wants to be an electron neutrino. But yeah, we can classify a neutrino into these different types as well. Now, I mentioned regression, which is basically just predicting a value. So on top of classifying, hey, we found a neutrino or we didn't, we can also predict where the neutrino is coming from these maps. So we can predict the azimuth angle and the zenith angle. Now, if we go back to this, this is really easy to predict. If we had a more accurate representation of what a neutrino would really look like, you wouldn't be able to tell where it's coming in. So what's nice about using a vision transformer is that it can hopefully find that with higher accuracy than a human would be able to do. But we predict where it's hitting the ice, and then if we have that information, we can predict the energy of these particles as well. Also, some other current neutrino projects. We have RNOG, which is the Radio Neutrino Observatory in Greenland. We have IceCube, which is in Antarctica, and then we have RSM, which I don't know where that is, but that's OK. Somewhere with ice. Ice is very important for these projects. The reason that we go to places with ice is basically when a particle hits a piece of ice deep in, let's say, Antarctica, the light needs to reflect through the ground, and it can't reflect through rock, because rock is solid and has a reflection gradient, I think, of like 1. So it doesn't, you can't see any light. But if you have light traveling through ice, it gets through the ice. So that's why we do all our experiments in very icy places. There is a project in the Mediterranean Sea, which is pretty cool. They basically stick a bunch of lines in the sea really deep down with like globes on them. And the fish swim around. They don't care about whatever those electronics are. But instead of using ice, this experiment tries to use the reflection of particles, or reflection of light in water. OK, any questions? Yes?
So I knew it was almost always in ice. I don't understand what the advantage of ice over water is. Is it just stability? Things stay where you put them?
I would say probably there's a variety of factors. Funding is one thing. Also approval. So Antarctica is approved for research. The Mediterranean Sea is less so. Also, it depends on what you're building. So we put antennas in, IceCube puts antennas deep in the ice. We're able to fly a balloon around Antarctica. And why we chose Antarctica is because when you take a balloon, like when you inflate a balloon, it'll travel around the South Pole. So the Earth is spinning, right? Then the winds are going around the pole. So you wait just a little bit of time, and the balloon will just come back to you. You don't have to like go find it. So that's pretty nice. And then there's ice in Antarctica as well, so you get kind of both. It's pretty nice.
Thank you.
Yeah, so you said that one of the values of neutrinos is that they carry information.
Yes.
Is that correct?
Yes.
Okay, so trying to figure this out. So that sounds like a way to, and then like you're trying to find the direction that these things come from.
Mm-hmm.
Is that like kind of to create like, I saw something somewhere, like a basis where there's one reaction and there's another equal reaction somewhere in the universe or something?
It's more so to, sorry, continue. It's more so to just map. So if we know that a neutrino is coming from this direction, we can say, oh, let's point our telescopes over there. Let's look like with high definition in this direction. And then if we take good measurements in that direction, we hopefully can learn more about, maybe it was a supernova, study interesting things about supernova, or maybe it was a AGN, or an active galactic nuclei, which is basically galaxies. We can learn more about that. So it's kind of, it helps map the universe.
What about like reality? Like, yeah, so you talk about carrying information though. Like, what information I know it helps us understand the universe and what information can be carried on neutrinos or used in terms of distance and measurement. And do you know any?
Yeah, the information that we would be looking at is, like I said, the direction of where the particle's colliding, and also the energy. So if we know the type of energy, and I guess the type of particle, so whether it's a muon neutrino, electron neutrino, tau neutrino, that will also help us understand, hey, which cosmic body might have produced this. And then if we study these cosmic bodies, we could learn about how they're formed, and from there, hopefully, more about how the universe began.
So we know the types of reactions that create neutrinos. We do not know the objects that create ultra-high energy neutrinos. And if you just say, hey, someone dropped a pot of gold in front of my house. Cool, right? That is so awesome. But you want to know where it came from so you can figure out how to do it again.
Yeah.
So in a way, we're looking for these things. So like, is it that these supermassive black holes are creating jets of particles that are sending stuff at us, and that's what creates these things? Or is it a type of event that we don't understand in the universe? And that's the thing, is we don't know the answer to that question.
Two questions. Do the neutrinos keep going on and on and on forever in infinity? And the other question is, are some of them regular matter and some dark matter?
These would all be regular matter, I believe. The direction of the neutrino, they're going to keep going until they collide with something, or until, I mean, I guess they're unperturbed by space, so they'll just keep going until they run out of energy. So they've got some kinetic energy associated with it when they're shot out of these cosmic bodies. So they just keep going and going until they collide with something, and hopefully they collide with Earth, and we can detect them.
How much of this is actually theoretical versus practical? Because you say hasn't been captured on these, like these pixels. I think of them as these little pixels.
Yeah.
Pixels with numbers. So you had to use a simulation.
Yes.
So is most of this theoretical, or?
There have been experiments which have captured neutrinos, not extremely energetic neutrinos. I think there's one called the oh my god particle, which it's not a neutrino, but it's a really high energetic particle that doesn't make any sense why it should exist. That was read, but we know that they exist and that they are coming with high energies, but like Wayne said, we don't necessarily know what is creating them. We have ideas about what theoretically could, just from knowing other things about cosmic bodies. Then the reason that we use a simulation, like you said, is we have not detected neutrinos with with ANITA 3. So in order to get a big training data set for our models, we have to use simulated data. So I'm talking like 200 to 300,000 images that we put into this model, or put into this to make this AI, and we don't have 200,000 to 300,000 neutrinos that we've detected. So we have to use a simulation in that case.
So would the input be incorrect, or bias in the input?
There absolutely can be a bias in the input. And one thing that we're trying to do to mitigate that is to use an accurate energy model for the neutrinos that are simulated. And that comes from other science, which I'm not a part of, but I trust them. Yes?
Would you be able to tell where voids, like cosmic voids are, or using this because when the neutrino just passed through, you wouldn't be able to tell if there's nothing in this area, you would just see stuff beyond that, or could you tell, like, since the sequence is long, or whatever, based on that work?
As opposed to like a cosmic void, I guess because the neutrinos act more as just like a straight line to where they were output. I mean, probably not exactly straight. There's going to be some perturbation of space. But if we do later analysis based on where the neutrinos are coming from, we could probably figure things out like that. But initially, from just knowing, oh, there's a neutrino here, and this is its energy, and this is the flavor, no. Yes?
So you're down in Antarctica. I mean, would these, if
Mm-hmm.
Would core samples show any evidence of this?
Unfortunately, no, because it's a active event. So a neutrino hits a piece of ice, and then radio waves are sent out. They'll keep being sent out, but we won't really be able to tell that a neutrino hit a piece of ice if we take out the ice later.
So the type of radiation that we're looking at is very similar to Cherenkov radiation. So like the nuclear reactors we know are associated with that blue color. That is electrons and other particles going faster than the speed of light in water that are going through and creating light. And so that's effectively what's happening is a neutrino will hit something, it's very high energy, and it will scatter particles and other things through the ice. One way to detect that is the visible light in ice cube. So that means wherever we put those photomultiplier tubes, those light detectors, we can see that piece. The NITA is trying to look at a different wavelength so that they can survey more ice and see more things, and that's where the radio wavelengths of that light that was produced are then observed by the balloon experiment.
Thanks, Wayne.
Well,
no, that's fair, and that is honestly the fundamental question of all research. What is the practical application? Honestly, for most people, I feel like the answer is none. Unless you're curious about the origin of the universe, then I guess that's a good practical application. But I would say in your daily life, you will not care about neutrinos.
So a lot of people, this is fascinating. So the director of the Center for Cosmology and Astroparticle Physics, John Beacom, he came into Astro Coffee one day and was talking about how they were using these particle detectors in Egypt. And it was like, okay, so why would anybody care about random particles coming from space? Well, these random particles coming from space create showers of particles that come flying through the flying through the atmosphere. And they were using these particle detectors to map out the pyramids. Because some particles go through rocks, other particles don't. So if you are measuring the amount of things that are going through different parts of the pyramid, you can literally measure when and where voids happen and can map out all of the structures from within the pyramids. So particle physics doesn't have any impact at some level on our daily lives until it does. Which is just really cool. So as we get better, we may have to use it.
well, Jack, thank you so much for this presentation. And if anyone does have questions, if you want to stick around and ask, the library is closed, but the store is open. And then when it gets dark enough, as long as it's clear, if you want to hang around, we'll get the telescopes out and see what we can find. Thank you all for coming.